All right. Good morning, everyone. I, as always, have good news and bad news. Well, first of all, let me start by saying that this is going to be the last lecture. And I leave it up to you to decide whether that's good or bad news. But to add some good news to that, we're going to solve a nice problem. Because we're going to talk about experiment design for system identification, as Kanat already announced. So this is the outline of this part of the lecture. I'll start by talking about this problem of experiment design. Also reminding you of certain things we've already studied before in the course, like the fundamental lemma. I briefly then want to recap the conditions for informativity for system identification. And then finally, we'll design the shortest experiment for linear system identification. Okay, so let's start. Well, we're going to consider input state output systems. U, again, is the input, X is the state, Y is the output. We have n true states, so X of t is a vector in R n true. M inputs and P outputs. As before the break, we're going to assume that the state space dimension of this true system is unknown. So we do not know n true, and we also do not know the parameters of the model. So we do not have access to these matrices A true, B true, C true, and D true. I do assume some prior knowledge, which I will introduce shortly. But let's talk first about the high-level goal. So what do I want to achieve? So in this lecture, I want to design inputs, U, 0 up to t minus 1, in such a way that the resulting input-output data allow me to uniquely identify the system. So I design these inputs of the experiment. I apply those inputs to my system. In the end, then, I'm going to obtain this input-output data, Uy, and I want to guarantee that my choice of inputs is correct, in the sense that after collecting all these data, I can indeed identify the system. That's my goal. So, before I can formally state the problem, let me remind you of one thing. So remember that we, as before, considered this observability matrix, omega k, containing these matrices C through A, up to some depth A to the power k minus 1. And then we define the lag to be the smallest integer L, greater or equal to 0, such that the rank of omega L is equal to the rank of omega L plus 1. And I will denote the lag of this true system by L true. Again, by Cayley-Hamilton theorem, the true lag is always less than or equal to the true state space dimension n true. Okay. Now, I'm going to assume the same prior knowledge as we assumed before the break. So, Kanat already introduced this prior knowledge. We're going to assume that our true system is controllable and observable. And we also assume these bounds on the lag and the state space dimension. So I know that L true over here is less than or equal to capital L. And N true, the true state space dimension, is less than or equal to capital N. And I know capital N and capital L. So my question is going to be, how do I design these inputs now in such a way that the resulting data enable system identification? In other words, such that the input-output data are informative for system identification. That means that the goal is to identify the true state space dimension and true from the data. And also, I want to be able to identify matrices A, B, C, and D that are isomorphic to the true system. In other words, they only differ from the true system matrices by a state space transformation. And that state space transformation is given by this non-singular matrix S. That's the goal.
We know capital N.
Yes, we know capital N. Yes.
What choose L to be equal to N?
Yes, in principle, I suppose that you have this upper bound on the state space dimension and you don't know what the lag of the true system is. Then you can take capital L to be capital N. But in some cases, you may have a bit more prior knowledge. So you know that this L true is strictly smaller than capital N. Then you can incorporate that extra prior knowledge using this capital L. Yeah, indeed. Are there any other questions? No? Okay. Well, you may ask the following now. So on day one and also later in the course, we already studied this fundamental lemma by Willems and co-authors. And you may now have the question like, yeah, but can't we just apply this fundamental lemma to this problem? I designed this input U to be persistently exciting. And then surely, if I take my input persistently exciting of sufficiently high order, I can use subspace identification to obtain these A, B, C, D matrices. Right? So let's have a look how that went again. So I remind you of the fact that the input U is persistently exciting of a given order K if the Hankel matrix of this input of depth K has full row rank. In other words, I construct now this Hankel matrix of U in this way. And for U to be persistently exciting of order K, that Hankel matrix needs to have rank K times M. Full row rank. So, one of the possibilities now to generate this experiment is in the following way. I choose my T to be this number here on the slide. So this is the time horizon of the experiment, right? I design my input U to be persistently exciting of sufficient order, namely N plus L plus 1. I apply that input to my system. It generates some output data, Y, on the interval 0, T minus L, T minus 1, sorry. And then by the fundamental lemma, it follows that the rank of this input-output Hankel matrix is L plus 1 times M plus N true. So I have this sufficient high rank on the input-output Hankel matrix. Yeah, and then I can apply subspace identification methods to identify A, B, C, and D. Well, just to make one small connection to the lecture on Monday, there I explained that to apply this subspace identification method of Mark Monen and co-authors, you needed actually persistently exciting inputs U of order 3n. But it turns out that one can also tweak the scheme that they have, and one can work actually with persistently exciting inputs of slightly lower order. Namely, you only need persistency of excitation of order n plus L plus 1. I did not explain that on Monday. It's a bit of a technical argument, but the bottom line is, instead of working with persistently exciting inputs of order 3n, you can also work with this order by making some modifications to their scheme. No? But I hope you agree now that this would be one way to generate an experiment from which finally you can identify the system up to state space transformations. But you see that one of the downsides of that possible solution is that you have to choose this t, so the time horizon of the experiment, to be fairly large. So my question, or maybe before I ask that question, I could consider an example. Let's do that. So I have this simple example of a two-dimensional system. So let's take these matrices. I take A true to be the one over here, so 0, 1, 1, 1. This is B true. C true is the matrix over here, and D true is 0, 2. Let's also consider some initial state, x0, like that. In this case, we have that n true is 2, right? We have two states. The true leg of the system is 1, in this case. And the reason is that already the observability matrix of depth 1 has full row rank. Let's suppose that we have upper bounds on the true state space dimension and the true leg. And in this case, I take them both 2. So this would be a situation where you do not indeed have more information on the leg. Right, we just take this upper bound L to be equal to capital M. Okay, what do I have to do to follow this pipeline that I highlighted in the previous slide? Well, in this case, I need to choose T to be 9. U needs to be persistently exciting of order capital L plus capital L n plus 1, so 5. And one input that does the trick, I mean, there are many different choices, but for instance, you could choose the input U08 to be 1, 1, followed by zeros, by 1, and zeros. This is an input that is persistently exciting of order 5. Maybe you don't see that immediately. I also don't see that immediately, by the way. So I have to do that. But the point is that if you look at the Hankel matrix of depth 5 of this input, well, what is that? 1, 1, 0, 0, 0, right? 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. Right? Then 0, 0, 0, 1, 0. And finally, 0, 0, 1, 0, 0. So in this case, this is the Hankel matrix of depth 5 of the input. Yeah, indeed. Now you see that indeed this matrix has full row rank. So the input is persistently exciting of order 5. Okay. Now I apply that input to my system. I get the output data. And my input-output Hankel matrix is the one that we have over here. We can again compute the rank of that input-output Hankel matrix, and that turns out to be 5. From there, I can actually deduce the true state space dimension of the system. Right, because if you go back one slide, by the fundamental lemma, that input-output Hankel matrix must have rank L plus 1 times M. So this is 3 in our example, plus the true state space dimension. Meaning that n true must indeed be equal to 2. Right. And then finally, I can use these data, this input-output Hankel matrix, to identify A, B, C, and D. Now, the big question, of course, in my opinion, is now, I could, of course, go through this procedure, apply this persistently exciting input, but is this somehow the best that we can do? And what I mean by best is this the smallest number of samples, t, that I can achieve? So necessarily for you to be persistently exciting of this order, you need this many samples. But are there experiments with less samples for which you can still identify the system? That's the question. Well, this would not be a very interesting lecture if it turned out that this was the smallest possible number of samples. So indeed, it turns out that the answer to this question is no. So this is not the smallest possible number of samples. And one way of improving over this persistency of excitation is actually, instead of doing an offline procedure, where before doing the experiment, I already design all of my inputs at once, right? So, for instance, in this example, right? Before collecting any data, I could design my input U to be persistently exciting of order 5, right? I just need to choose this sequence of inputs in such a way that this Hankel matrix has rank 5. So this procedure, obtained from the fundamental lemma, is in principle completely offline. First, we design the sequence of inputs, then we apply these inputs to the system, we collect the output data, and that's it, right? So sometimes people refer to this as offline experiment design. One way of improving over the fundamental lemma is to, instead of doing an offline procedure, to run an online experiment. So let me try to explain to you what do I mean by an online experiment. The idea is going to be in the rest of the lecture to do the following. So instead of choosing these 9 inputs all at once, so that we have this persistency of excitation condition, I'm going to do the following. So I just choose the first input of my experiment. Let's say U0. Right? And then I apply U0 to my system. Well, what is my system output? Of course, y at time 0. And now the idea is going to be that I can already use this partial data, so U0 and Y0, to design the next input to my system. So I'm going to use these, right? So this U0 and the Y0. To generate a new input to my system, U1. And I'm going to apply again U1 to my system. That generates some output Y1. Now I'm going to repeat the story, so I'm going to use U0, Y0, U1, and Y1 to generate the next input sample of my experiment, so U2. And I continue doing that. And so that's what I mean by online. Instead of applying, first finding this whole batch of inputs, 9 at a time, applying them to the system and getting this output, I just apply one input, get the output, and on the basis of that partial data, I generate my next input. As we will see, that is very helpful because it's for the following reason. This first output of the system already tells me something about the system dynamics. And that's going to help us to generate the next input to the system And hopefully, well, I can already spoil it, using that we can improve this number of samples. Let me ask you a question. Does it make sense what I mean by online experiment design? Yeah, so I'll come to that indeed. I just want to kind of explain the idea. So indeed, that's a good question, right? So there are many schemes, of course, to take these two samples and to generate this next U1. So somehow we should come up with a clever way, of course, to generate this U1 now on the basis of this partial data, right? But I'll come to that indeed, yeah. We're going to use the Y0 to design the next sample of the input. Yeah. Yeah. Other questions at this stage? No? Okay, let's continue then. Well, I want to talk a little bit about, maybe this is a little bit of shameless self-promotion. I'm sorry, but it's really relevant for the story. Yeah? So a couple of years ago, I wrote this paper on this online experiment design method. So I want to talk about an alternative to the fundamental lemma using data that's collected online. So we saw already one possible solution to the problem using persistently exciting inputs. And now from this paper, I'm going to consider another possible solution to the problem. So, what is that solution? Well, I'm going to design the input U of t in an online manner, as I illustrated on the board, based on the samples that I collected before. So, I'm first going to apply U0. I get Y0. And then given U0 and Y0, I'm going to design the U1. Then I collect the Y1. I now have U0, U1, Y0, Y1. And I generate the next sample, U2. And I continue doing that. So, it turns out that if one applies that procedure from the paper to generate this input, then the number t of samples that one needs to identify the system is not specified beforehand. But after applying this procedure from the paper, at a certain point the procedure terminates, and it's exactly after t is L plus 1 m plus n through plus L steps. So within the paper, I will not show you the details, but the idea is, again, you design these inputs online. At a certain point, the procedure stops, and it stops after exactly this number of steps. So from that stopping criterion, you can then also read off the true state space dimension, right? Because beforehand, I did not know what n true was, but since I know, since we proved actually, that the procedure stops after exactly this number of steps, I can now compute n true, right? It's just t minus this number minus this number. Huh? And then one can again apply subspace identification to find A, B, C, D. Very good point. Yeah, indeed. So, okay, this is a nice observation. So, what I did not know at the time of writing this paper is that one could vary this depth of the Hankel matrix. So here I was always working with a fixed depth Hankel matrix of depth L. But indeed, what turned out later to be the case, which followed from the paper of Kanat and Paulo, is that one can even improve this depth L of the Hankel matrix by indeed studying this LA, this actual bound on the leg, which can be smaller than this step L. Yeah, so that's indeed a nice observation. I will come to that actually. That's going to be necessary to generate really the shortest experiment. Yeah. Let's consider also an example of this online method. So I study the same system as before, initialized in the same initial condition. Well, it turns out that using that online method, the first 3 inputs you can choose arbitrarily, but not all 0. So I choose them as 1, 0, 0. And we measure the corresponding outputs of the system, like this. Then we consider an input-output Hankel matrix of the data. And the idea of this online experiment design is to increase the rank of this input-output Hankel matrix at every step. So using this data, I just have 1 column in my Hankel matrix, right? Now I want to choose the inputs in such a way that at every step, while adding 1 more sample, I add 1 more column to this Hankel matrix, right? And I want to choose this input in such a way that I always increase the rank of the Hankel matrix at every time step. So already here we have 1 column. The rank is obviously 1 because this is a non-zero column. And let's now add another column to this input-output Hankel matrix. So I have then the input-output Hankel matrix over here. Well, how should I choose U3 to increase the rank? Well, obviously, if you choose U3 non-zero, then you increase the rank, right? Then we have 2 linearly independent columns. If I choose U3 in a slightly silly way, if I would choose it 0, then of course this whole column would be 0, and I would not increase the rank. But if I choose it in a sensible way, namely U3 is not 0, then indeed I increase the rank. So I do that. I choose U3 to be 1, and then indeed you see that in this second step I have a rank 2 matrix. Okay, I measure the corresponding output, and then I continue 1 step further. So now I consider 3 columns in my Hankel matrix. It turns out that here you could choose U4, so the 4th input, arbitrarily. So for any choice of U4, you will increase the rank of the Hankel matrix. Always this Hankel matrix has the rank 3. So I just choose U4 to be 0. Okay. Increase again, so I go to time step 5. Also in this case, you can see that for any U5, the rank of this Hankel matrix is 4. So again, I choose U to be 0. Finally, 6th time step. Again, I can take U6 to be 0. Now something interesting happens. So at time step 7, so U at time 7, I see that no matter which input I apply to the system, the rank of this Hankel matrix will not increase. So no matter which input I apply, always I get that this rank is 5. That is the moment where the stopping criterion is activated. So at that moment I stop my online procedure. And then we get the following result, namely the data up to time 6 satisfy this rank condition, namely that the rank of the input-output Hankel matrix is 5. And from here, again, we can identify n true. I want to stress one aspect, which I swept a little bit under the rug about this online experiment. So if we look at this Hankel matrix, I have here 3 rows of the inputs and 2 rows of the outputs. Instead, before I was considering these Hankel matrices with the same number of rows for the inputs and outputs, or same number of block rows of the inputs and outputs. So that's somehow curious. Huh? Why do you think that something like that would be needed? Why can't I simply work with a depth 3 Hankel matrix of the inputs and outputs in this online procedure? So why should I change? Let's look at this one, for instance. Suppose that I would instead consider the depth 3 Hankel matrix of the outputs here. Then this Hankel matrix would also contain y at time 3. But how am I going to choose u at time 3 then? Because y at time 3 depends on u at time 3. And so I cannot work with this depth 3 Hankel matrix of both the inputs and outputs. And that's kind of the reasoning why I take here, instead of a depth 3 Hankel matrix of the output, a depth 2 Hankel matrix of the output. But the conclusions in the end are going to be the same, because if I can make this Hankel matrix rank 5, then also when I add the final row of outputs, I still have a rank 5 Hankel matrix. So the reason for working with this slightly adapted Hankel matrix is because, of course, this last output depends on the last input. Okay. Just to give some intuition. Okay. Let's continue. So what did we conclude using this online scheme now? Well, in this case, I can work with 7 samples of the inputs and the outputs. So we have reduced the number of samples as compared to the fundamental lemma from TS9 to TS7. Right? So you see that indeed, using this online procedure, choosing the inputs one by one and measuring the corresponding outputs, I can already reduce the number of samples. But now I go back to my original question. So I ask again about this online procedure. Is this now the smallest number of samples? Yes or no? Can we somehow prove that this is the smallest number of samples, or is it maybe not the smallest number of samples that I can achieve? Well, for the moment, I keep the answer to that question a secret, but you will see the answer in a few minutes. Okay. Well, to really get a full answer to that question, what I need are conditions, necessary and sufficient conditions for informativity for system identification. Exactly the ones that Kanat has described before. So I want to briefly recap those conditions for informativity. So this is from the paper by Kanat and Paolo. For the moment, I will study the case that my UI data are arbitrary, so I do not make any assumptions on the input. And indeed, the question is, under which conditions on these input-output data can I uniquely identify the true system? Okay. Well, since this is a technical subject, I just want to remind you of some notation that we used. So we identify state space systems, A, B, C, D, by these matrices A, B, C, and D. And these are for systems of arbitrary state space dimension n, greater or equal to 0, but with a fixed number of inputs m and a fixed number of outputs b. I denote all of these systems by this set S. So S contains all input state output systems with exactly P outputs, exactly M inputs, and an arbitrary number of states. N is greater or equal to 0. We can also consider the subset of those systems, of systems that are observable. And we use a notation O for that. Yet another subset of that set of observable systems is the set of minimal systems. So those are systems which are both observable and controllable. We will also use the set Sn of state space systems with exactly n states. And SLN denotes those systems with exactly n states and lag L. Okay. Good. This is a definition we already saw before the break. It's a very important one, though. So we say that the system ABCD explains the data or is consistent with the data if there exists some sequence of states, x from time 0 up to t, such that this equation is satisfied. By the set E, I denote all systems that are explaining the data. So these are all A, B, C, D in S, for which A, B, C, D explains the data U, Y. So these are all systems consistent with the data. And in general, that set consists of state space systems of various different state space dimensions. Right? But I also denote the set En of all explaining systems with precisely n states. So that's the intersection of the set of explaining systems and the set Sn of state space systems of exactly n states. Similarly, you can also look at systems that are explaining the data of precisely n states and lag L. And we denote that by this set ELN. Again, those are explaining systems with exactly n states and lag L. Now, the true system had lag L true and state space dimension n true, which means that this system A true, B true, C true, D true is in the set E, L true, N true, which is a subset of all explaining systems of n true states, which finally is a subset of all explaining systems, right? By definition. Okay, very good. Wow. Kanat had a nice example on the board before the break showing that system identification is not possible without any prior knowledge. So without an upper bound on the state space dimension, we're completely doomed. So we need some prior knowledge. I will denote by SPK the subset of S, so subset of state space systems, of all systems complying with my prior knowledge. And in particular, the true system is assumed to have that prior. Well, what is this set SPK in our setting? Well, I remind you of the fact that we assumed upper bounds on the state space dimension and the lag of the true system. So we have these numbers, capital N and capital L. So that must be part of the prior knowledge. Meaning that if we define this set SLN of all systems A, B, C, D with lag less than or equal to L and state space dimension less than or equal to capital N, then my true system must be within SLN. It indeed has lag less than L, state space dimension less than N. But in addition to that, of course, we have the prior knowledge that our true system is both controllable and observable, which means that this set SPK is exactly the intersection of minimal systems, both controllable and observable systems, and the set SLN of systems with lag less than L, state space dimension less than N. Good. Well, using that, we had the following definition. So the data UI are informative for system identification if two properties hold. So the first property is that on the basis of the input-output data, one is able to determine the state space dimension of the true system. Let's have a look at what that means in terms of formulas, right? So, all explaining systems which comply with the prior knowledge, so if I look at the intersection of explaining systems and a set of prior knowledge, so all explaining systems that comply with the prior knowledge have exactly n true states. That's what the first line says over here. And since all explaining systems complying with the prior knowledge have n true states, I'm able to indeed identify n true from the input-output data. Second property we need for the data to be informative for system identification is that any two systems that are explaining the data and satisfy our prior knowledge are related by a state space transformation. In other words, they're isomorphic. If these two properties hold, then we say the data are informative for system identification. Because if these two properties hold, from item 1, I'm able to identify the state space dimension of the system. And then by item 2, I'm able to identify the true system up to a state space transformation. That's the reasoning. Okay. Well, to formulate necessary and sufficient conditions for informativity for system identification, these two numbers were involved, L-min and N-min. What was L-min? Well, this was the minimum lag of any system explaining the data. And similarly, N-min denotes the minimum state space dimension of any explaining system. For any explaining system with L lag and N state space dimension, we have the following inequality. So N minus L is always larger or equal to N min minus L min. If you then take L to the other side, you see that the lag of any explaining system is upper bounded by this number over here. N min and L min I can obtain using the data. And furthermore, N I can upper bound by this number capital N over here. That means that using the data, I can obtain also a bound on the lag of the true system. So that's the data-guided bound given over here. So LD is a bound on the lag of the true system. In some situations, that data-guided bound on the lag is better than the given upper bound that we had before. That means that we can actually improve the upper bound on the lag, in some cases, as follows. So I take the minimum of the bound on the lag that I already had, the capital L, and the data-guided bound on the lag, LD, and that's my actual bound on the lag. Well, using that actual bound on the leg, Kanat and Paulo formulated then the following theorem. So the data are informative for system identification if and only if T is sufficiently large and the rank of the input-output Hanko matrix of depth LA plus 1 is equal to LA plus 1 times M plus N min. So these were the necessary and sufficient conditions. Note that in this condition, the depth of the Hanko matrix is determined from the data because it depends on this actual bound on the leg, which depends on the data, because it depends on N min and L min. Okay. Yeah, moreover, if these conditions are satisfied, then L min coincides with the true leg and N min coincides with the true state space dimension. Okay, let's now consider experiment design again, after considering these conditions for informativity. So these were the conditions for informativity for system identification. Since if the conditions are satisfied, L true is equal to L min and N true is equal to N min, I can do the following. So if the data are informative for system identification, I can substitute L min is equal to L true here, N min is equal to N true here, and I can define this boldface L, which is the minimum of L and N true minus N true plus L true. Since necessarily for informativity for system identification, the rank of this input-output Hanko matrix must be this number over here, then I see that the shortest possible input-output experiment has exactly this number, boldface T, number of samples. So using this theorem, we now come up really with a lower bound on the number of samples that we need. It is impossible to design an experiment that is informative for system identification with less number of samples than this number over here. So this is a lower bound on the number of samples we need. But now the very important question is, is it even possible to generate now informative data of length exactly this lower bound? And so can I design my inputs in such a way that I achieve an experiment which is informative for system identification with exactly this lower bound number of samples? That is a very difficult question in general because this number T, smallest possible number of samples, depends on N true, the true state space dimension. And I don't know that beforehand. Even worse, I don't even know the depth of the Hanko matrix, L plus 1, that I should look at, because also this number, boldface L, depends on N true and L true. So it's really non-trivial to answer this question, and at this point, we don't know whether it's possible to generate an experiment with exactly this number of samples. And the point is, of course, that I don't know N true and L true before doing this experiment. But miraculously, we will see in the next few slides that indeed it is possible to design an experiment of exactly this length. Curious, huh? So, let me finally then show you how to do that. So, since I'm going to work in an online manner again, adding columns to my Hanko matrix, I need a little bit of notation. So I denote the Hanko matrix at a certain time t, since we're going to update this, by hkt. So this is the Hankel matrix up to some time t. And similarly, I also define the matrix GKT to be this Hankel matrix with the last row removed. So GKT is just this Hankel matrix, but I removed the last row of outputs. Similarly, I can also define L min at a certain time t, N min at a certain time t. So these are the numbers L min and N min determined on the basis of the data up to time t, and the actual bound on the lag, LAT. So what's the main idea now? Well, since I don't know the right depth of the Hankel matrix, this L plus 1, my idea is the following. So I just start with the simplest Hankel matrix that I can imagine. Just one row. So I start with k as 1. And I will iterate between the following two steps. So for this depth 1 Hankel matrix, I will try and increase the rank of the GKT matrix. So this matrix over here. So this is a similar procedure as in the online experiment that I showed you before, right? So we try to improve the rank of this GK Hankel matrix until I cannot make any progress anymore. If I cannot make any progress anymore, I then increase the depth k by 1. So from k is 1, I go to depth 2 Hankel matrix, and again I increase the rank of the GK matrix. And I continue doing that. Yeah, but of course the important question is when to stop that. At a certain point I would like to stop and conclude that my data are informative. So how to do that? Well, to conclude that I need two lemmas. So first of all, one can prove that the rank of GKT is always less than or equal to m plus the rank of hk minus 1t. That means that there are two situations. Either the rank of GKT is strictly less than this number on the right, or it's equal to it. Right? Well, let's have a look about the first situation. So suppose that the rank of GKT is strictly less than the right-hand side. What did we prove? In that case, we can always increase the rank of the GK Hankel matrix in that case. Because, what is the statement of the lemma? Well, the lemma says the following. So if we have this strict inequality over here, there exists this m minus 1 dimensional affine set, AT, such that whenever I pick my input to not lie within this set, I increase the rank of the GK Hankel matrix. Right? So as I was saying, we consider two situations, right? Either this rank inequality holds strictly, and in that case, I can always increase the rank of my Hankel matrix, GK. Now let's have a look at what happens when I have equality over here. So, we have the following theorem. It says the following. So suppose that my input-output data are such that the Hankel matrix HK has full column rank, and now I have that the rank of GKT is equal to the right-hand side. Over here. Then the theorem says the following. This is arguably the most important point. So if we have that k is equal to LA plus 1, then let's have a look what happens. Then the depth k is exactly the right depth, L plus 1. The number of samples is exactly equal to the minimum number of samples that I need for system identification, and the input-output data are informative for system identification. But this is great, because this precisely gives me the stopping criterion. If this rank condition holds, I simply need to check whether my K is equal to LA plus 1 or not. If my K, so the depth of the Hankel matrix that I'm considering, is indeed LA plus 1, we're done. Because by the theorem, then the data are informative for system identification. Now, so this is the important point. The theorem gives you a way of stopping this procedure. Stopping the procedure of increasing the depth of the Hankel matrix, increasing the rank, again increasing the depth, and so on. Because if K is equal to LA plus 1, then I know I need to stop. Cool, huh? So, if I put then everything together, we constructed this online experiment design algorithm. Yeah, okay. I don't want to show you all the details. I realize this is a bit difficult to read. But let me point out the following main aspects. So, we have this while loop that checks the stopping criterion. So this checks whether indeed K is equal to LA plus 1 or not. While the stopping criterion is not satisfied, of course, here in this inner while loop, I'm going to increase the rank of my GK matrix by choosing these inputs to not lie within this affine set, AT. As long as I can do that, I increase the rank, and then I go back and I increase the depth, K, of my Hankel matrix, as long as the stopping criterion is not satisfied. That's the idea. Okay. Well, instead of looking at the algorithm, let me have a look at one final example of this. So I consider the same system as we had before. N true was equal to 2, L true was equal to 1, and we had these upper bounds on the lag and the state space dimension. In the online experiment design, again, I just apply one input to my system. So I choose U0 to be 1, and I collect the corresponding output, Y0. According to my algorithm that I showed on the previous slide, I set T to be 1, and the depth of the Hankel matrix to be the simplest one possible, just 1. We always start with the depth 1 Hankel matrix. Well, we then have to check the stopping criterion. So what do? I compute N-min and L-min at this time. In this case, it turns out that they're both equal to 0. Means that the actual bound on the lag is the minimum of these two numbers, the minimum of 2 and 2, which is 2. That means that typically 1 is not equal to 3, so the stopping criterion is not satisfied, right? So if the stopping criterion is not satisfied, what we do is we increase the depth of the Hankel matrix to K is equal to 2. In this case, something interesting is happening. Because K is equal to 2, and I only have one data point, I do not have enough data to fill my Hankel matrix. In this case, you can choose U to be arbitrary, and we measure the corresponding output. Okay. Now the idea is, for this fixed depth 2, to increase the rank of the Hankel matrix. So how to do that in this case? Well, for time 2, I just choose U2 to be non-zero, right? Let's say 1. Then I continue here. I can choose U3 to be 0. U4 also to be 0. And now I achieve the maximal rank possible at this depth. Because we have 4 rows. In that case, this rank inequality that we considered before holds exactly. So the rank of the G matrix is exactly M plus the rank of the H Hankel matrix. And then we have to check the stopping criterion again. So L min in this case is 1, N min is 2. that means that the actual upper bound on my leg is the minimum of these two numbers. It's equal to 1, which means that at this point, my stopping criterion kicks in. Because indeed, since k was equal to 2, this is equal to the right-hand side. Then our algorithm stops, and I know that my data are informative for system identification. Okay. What's the point then finally? Well, indeed here now, we only needed 5 data samples. So we reduced the number of samples from 9, which was the approach based on the fundamental lemma, to 7 with this online experiment design with a fixed depth Hankel matrix, to finally 5 with the variable depth Hankel matrix, which is in fact the shortest experiment. So this is actually the minimum number of samples that you can achieve. Okay. Now, let me conclude then. So, to generate the shortest experiments for linear system identification, you need 2 ingredients. First of all, an online design of the inputs. So always I choose my inputs on the basis of past inputs and outputs. And also an online adaptation of the depth of the Hankel matrix. Right? So we cannot work with this fixed depth Hankel matrix anymore. We vary it from depth 1 onwards. Working with a fixed depth Hankel matrix only yields the shortest experiments in particular scenarios, namely if this inequality holds. Now, the examples that I showed you before were, of course, meant to be simple, and 9 samples, 7 samples, 5 samples. But for slightly larger systems, the improvement can be also very large. So let's have a look at one final example. For instance, if I have 80 inputs, 10 outputs, and 100 states, and I take these upper bounds on the leg and the state space dimension, fundamental lemma requires more than 20,000 samples. The online design with a fixed depth Hankel matrix requires more than 8,000. And the shortest one only requires 5,850. So you see that the improvement, especially with respect to the fundamental lemma, is large. Okay. So then we come at the end of the lecture. And in fact, at the end of all lectures of this course, I finally want to thank you all very much for attending and participating in the course. So, thank you all. If I understood correctly, at 12 there will be another lecture.